So next thing that we're looking at is graphing rational functions. So first, let's define what a rational function is. And so a rational function is a function of the form, and they have it as capital R of X is equal to P of X over Q of X, where P and Q are both polynomial functions. And we have to say that Q is not zero. It's not the zero polynomial. We can't divide by zero. And the domain R is a set of all real numbers, except for those which make the denominator Q equal to 0. Okay, so for rational functions, our function may or may not have a vertical and horizontal asymptote. So let's talk about what vertical and horizontal asymptotes are. And then let's talk about how to find those. And then we'll go through, use those asymptotes to help us graph the functions. And so a horizontal and vertical asymptote. So first, let's look at the horizontal asymptote. And we already kind of, well, maybe we didn't. I'm going to say we kind of already did this, but we didn't. Let R denote a function. If X goes to negative infinity, or as X goes to positive infinity, the values of R of X approach some fixed number L. If they do, then the line Y equals L is a horizontal asymptote of the graph of R. Okay, so let's look at what that's saying graphically. So let's say that Y equals L is right here. And it could be the X axis, it could be below this, it could be anywhere, but I'm just arbitrarily putting L here. And we said it had a horizontal asymptote. And we denote asymptotes with dotted lines, but normally they're not on the graph, or they're not on the graph. It's just so that we know what's going on. And so what this is telling me is, as X is going off to negative infinity, my graph is going to start hugging this line. I'm going to start getting closer and closer to these Y values. And so it either can be above or below. So I could come down like this, would be an example of a piece. As X goes off to negative infinity, my Y value goes to L. It could look something like this, where it's on the other side. Same idea. As we're going off to positive infinity, as X goes to positive infinity, my Y value is getting closer and closer to L. And so that can be down there, or it could be above. It's not going to be both, because that would mean then it wouldn't be a function. And so remember, R of X, or R, is just another way of saying your Y value. Okay, so just to get used to the notation, this would be saying the limit as X goes to negative infinity of f of X, this is equal to L. So as X goes off to negative infinity, what is our Y value approaching, which is L? Same idea here for a horizontal asymptote. As X is going to positive infinity of f of X, this would also be going to L. So that is a horizontal asymptote. Vertical asymptotes, let's read through this and then we'll talk about that and show you graphically. They explain this a little differently than I normally do, but we can talk about it. So if X approaches some number C, actually they do say the same thing. Okay, so as we're getting closer and closer to some X value, C, the value, absolute value of our Y, R of X, is going to go to infinity. That is, R of X, our Y value, either goes to negative infinity, or our Y value, as we get closer to that X value, C, goes to positive infinity. Then we say the line x equals c is a vertical asymptote of the graph of R. Okay, so graphically, let's locate some x equals c. Let's draw a vertical line. And this is saying as x is getting closer and closer to c, as we approach this value of c, it's either going to be shooting upwards to positive infinity or downwards to negative infinity. And they can both on each side be coming up the same direction, or they could both be going down the same direction, or one can be going one way, one going the other way. But as we're getting closer to x equals c on the left and the right, our y values are shooting off to positive or negative infinity. Okay, so now we know what a vertical and a horizontal asymptote is and what's happening on the graph for those asymptotes. The question is, how do we find those asymptotes? And so it depends on if we're looking for a vertical asymptote or a horizontal asymptote. Vertical asymptotes, you find them by finding out where our denominator equals 0, but not also our numerator. So vertical asymptotes occur at, let's say, just x equals c, where x equals c sets the denominator equals 0, but not the numerator. So if we're looking for our vertical asymptotes, then we're going to have to factor both the numerator and denominator and see what value set the denominator 0, but not also the numerator. Note, if there's an x value that sets both equal to 0, it's not an asymptote, but it's not defined because we can never have our value set our denominator equal to 0 and be in our domain. And so it's not an asymptote, it's not defined. So we're going to have actually an open circle at that value. So an open point. So if there is an x value that sets both the numerator and denominator equal 0, then there is an open circle at that point. Okay, so let's look at an example where we're just trying to find the vertical asymptotes. Let me just pull one up really quick. Okay, so for the following example, we have this rational function q of x, and this is equal to, in the numerator, negative x times a quantity 1 minus x. That is all over, and in our denominator, we have 3x squared plus 5x minus 2. The directions asked to find the domain, and let's find the vertical asymptotes too. So let's first find the domain of f of x, not f of x, q of x. Okay, so we want to go ahead and factor our denominator. And so I'm going to actually do that on the side. So let's look at 3x squared plus 5x minus 2. So I notice my coefficient in front of x squared is not 1. So I'm going to try that AC method and see if I can factor it that way. 3 times -2, that's -6. So I'm looking for something that multiplies to -6, but would add to my middle term's coefficient of 5. And so -1 and +5, I'm sorry, -1 and +6 multiplies to -6 and adds to 5. So we're using 6 and -1. So the trick was to go in and rewrite your middle term using those two numbers. And so instead of writing 5x, we're going to write this as plus 6x minus 1x minus 2. Factor by grouping. So the first two terms, we're going to pull out a 3x. That's what they share in common. And we would be left with then x plus 2. The last two terms, we can pull out a -1. A lot of times I don't write -1, but sometimes students have a hard time if there's not that one there, they have a hard time and they drop it off when they factor out the parentheses. So for right now, I'm going to put it in there. And so let's pull out the x plus 2 from both groupings. And if we do, then we're left with a 3x from the first piece and a -1 from the second piece. And so we know that we can factor this. I still have -x all times the quantity 1 minus x in my numerator all over x plus 2 times 3x minus 1. So let's look at when is our denominator equal to 0. So that's when x is -2. So x cannot be -2. And when is 3x minus 1 equal to 0? Well, if I add 1 to both sides and then divide by 3, I get x is 1/3. So x cannot be 1/3. So I would look to see, are those values that set my numerator also equal to 0? And they aren't. And so those then are vertical asymptotes. I'm going to call it VA. So our vertical asymptotes are at, so you need to be careful here. When you're writing your vertical asymptote or your horizontal asymptotes, those are equations, those are lines. And so if a vertical asymptote, remember vertical equations are in the form x equals. And so when we write these asymptotes, don't forget to put the x or the y depending on which one it is. So this is x equals -2 is a vertical asymptote, and x equals 1/3 is a vertical asymptote. And so we have two asymptotes, vertical asymptotes on this. Okay, so let's take a break. And then I'm going to come back and I'll show us how to find horizontal asymptotes. And then we're going to put this together and start graphing these rational functions, which aren't that bad at all. Once we know on how to find these asymptotes, is actually pretty easy and kind of fun. Now we're going to look at finding horizontal asymptotes and oblique asymptotes. And I'll talk about what an oblique asymptote looks like in a moment. But consider that we have a rational function, our capital R of x, or given that we have some polynomial p of x all divided by some polynomial q of x. So this is just the notation we use before writing out a polynomial. So a sub n, x to the n, plus a sub n minus 1 times x to the n minus 1, ... plus a sub 1, x sub 1, plus a sub 0, all over. And then we just rewrote this as a separate polynomial function. So we used m instead of n, and we used b instead of a to be our coefficients. So consider this polynomial rational function r of x, in which the degree of the numerator is n and the degree of the denominator is m. So the highest exponent in the numerator is n and the highest exponent in the denominator is m. So there's three possibilities. Either the degree in the numerator is smaller than the degree in the denominator. And if that's the case, the degree of the numerator is less than the degree of the denominator, the line y equals 0 is a horizontal asymptote. So the line y equals 0 is the x-axis. The x-axis is going to be a horizontal asymptote if the degree of the denominator is larger. If you get that the degree of the numerator and denominator are the same, then y equals a sub n, the leading coefficient of the leading term in the numerator, all over b sub m, which was the leading coefficient of our leading term in the denominator, is going to be our horizontal asymptote. That is, the horizontal asymptote equals the ratio of the leading coefficients. So degree of the denominator is larger, it's y equals 0. The same, it's y equals a sub n over b sub n. If n, which is the degree of our numerator, is equal to 1 more than the degree of our denominator, we say that the degree of the numerator is 1 more than the degree of the denominator. The line y equals ax plus b is an oblique asymptote, which is the quotient found using polynomial division. Okay, so if our degree of the numerator is 1 more, then we're going to have to use long division of our polynomials to find out where is that graph hugging the line as x goes to positive and negative infinity. If the degree of our numerator is greater than or equal to 2 more, so the degree of the numerator is 2 or more greater than the degree of the denominator, there's going to be no horizontal or oblique asymptote, and the n-behaviors of the graph resembles the power function a sub n divided by b sub n, all times x to the n minus m power. Okay. So note, a rational function never has both a horizontal asymptote and an oblique asymptote. And a rational function may have neither a horizontal nor oblique asymptote. Okay, so finding the degree or finding the horizontal asymptote, we have to look at the degree of the numerator and denominator. So let's put this together and graph a rational function. Okay, so we want to graph t of x equals x cubed, all divided by x to the 4th minus 1. So let's find our vertical asymptotes if they exist. Let's find our horizontal asymptotes if they exist. Find our intercepts if they exist. What else do we want to do? And we also want to look at the domain. So first of all, let's factor. We need to factor the denominator in order to figure out what our asymptote, vertical asymptote is, if they do have any. Well, x to the 4th minus 1, that's a difference of squares, and we can break this down as x squared minus 1, all times x squared plus 1. So again, I noticed that one of those factors can be broken down further. X squared minus 1 is a difference of square there too. So we have x plus 1, x minus 1. X squared plus 1 isn't factorable over the real number, so we're just going to leave it as x squared plus 1. And so for our domain, x cannot be values which set the denominator equals 0, so -1 or 1. So our vertical asymptotes, those again occur values that set our denominator equals 0, but not also our numerator. So 1 sets our denominator equal to 0, but not our numerator, and same with -1. It sets our denominator equals 0, but not our numerator. So x equals 1 and x equals -1 are vertical asymptotes. Horizontal asymptote depends on the degree of the numerator and denominator. Notice that the degree of our numerator is 3 and our degree of our denominator is 4. So since the degree of the denominator is larger, it's blowing up faster. And so that y value as x goes to infinity or negative infinity is going to 0. And so we have a horizontal asymptote on our x-axis, y equals 0. Just want to note that a graph can never cross a vertical asymptote. Because, right, those are where it's undefined. A graph can cross a horizontal or a oblique asymptote. And if it does, it's just going to cross it, but still hug that line on the other side, most likely. So a graph can cross. Cannot, sorry. Cross a vertical asymptote. I'm just, again, going to call it VA just to save some time on writing. A graph can cross a horizontal asymptote. Okay, so let's put what we have so far, which are just our asymptotes. So again, we denote those with a dotted line. So our x-axis, let's just make it as a dotted line for now. And we have two asymptotes, vertical asymptotes at x equals 1 and x equals -1. So we have a dotted line coming through x equals -1 and x equals +1. Once you know where your asymptotes are, let's also find out what our intercepts are. Then we can pretty much go ahead and graph this. So let's find our intercepts. So if we look at the x-intercept, recall the x-intercept occurs when y is 0. So setting t of x equal to 0, we have 0 equals x cubed over x to the 4th minus 1. Really, technically, all we really have to worry about is looking at when is that numerator equals 0. Because we could, right, cancel out our denominator, because this is an equation, by multiplying both sides by x to the 4th minus 1. And so that would just leave us with 0 equals our numerator x cubed. Well, I could take the cubed root of both sides, but the cubed root of 0 is 0. So I know x is 0. So we know that we're crossing this x-axis right here. We're touching it. Our y-intercept, we're letting x equal 0. So we're looking at t of 0. So if we go in and we plug in 0 wherever we see an x, we got that 0 cubed all over 0 to the 4th minus 1. Well, 0 cubed is 0, and 0 over -1 is also 0. Okay. So to see what's going on with the graph, we just want to plot a couple of points on each side of a vertical asymptote. And that will kind of tell us which direction it's going. So let's plot some points. So plot a couple points on each side. of a vertical asymptote. So let's look at the left of x equals -1. So let's try x equals -2. And so if we look at t of -2, we'd go in there, we plug in -2 wherever we saw an x. So we got -2 cubed all over -2 to the 4th minus 1. Well, -2 times -2 times -2, -2 cubed is -8. -2 to the 4th power, that is 16 minus 1. So -8 over 15 is close to -1/2, but I know that this is less than 0. So I have this point below the x-axis here. So I pretty much know, actually, just with that one point, what my graph is going to look like because of the asymptotes. As I get closer and closer to this x equals -1, my graph, because it's below the x-axis and we didn't find an x-intercept over here, is going to be shooting downwards. So as x approaches -1 on the left, our graph goes to -infinity. Again, this is below the x-axis. I know I have a horizontal asymptote here. So as x is going to infinity, this is going to be going off to 0. It's getting closer and closer to y equals 0. Again, I know that's not above the x-axis because we would have found that as an intercept. So now we want to look at what's happening between -1 and 1. And so we want to plug in values to see, are we going to be above or below the x-axis? I know that that general shape in between x equals 1 and x equals -1 is going to be kind of a cubic type shape. I just don't know if it's above or below the x-axis where. So if we look at a point, the number between -1 and 0, so how about -0.5 or -1/2? If we do that, we get -1/2 cubed all over -1/2 to the 4th power. And we have -1. Well, -1/2 times -1/2 is 1/4. 1/4 times -1/2 is -1/8. All over -1/2 to the 4th power gives us +1/16 minus 1. Got a complex fraction. We can get rid of that complex fraction really fast by multiplying by a fancy 1 of our LCDs of the fractions within. And so LCD of 8 and 16 would be 16. So if we multiply 16 times -1/8, that leaves us with -2 in the numerator. Distributing my 16 to the denominator, 16 times 1 over 16 is 1, minus 16 times -1, so minus 16. So it looks like this is a positive number. It's above the x-axis. So this gives me -2 over -15, or 2/15. So in here, I know I'm above the x-axis. So I know because of my vertical asymptote at being at x equals -1, it has to hug this graph. It can't cross it. I'm going to come down here and I'm going to touch this x equals 0. And now I want to see, is it going to cross or just touch? Actually, what we just learned, if you looked at that 0, that was x cubed. That's an odd multiplicity. And so it's actually going to cross here. But we could test it, right, by plugging in +1/2 and show that that value we get back is -1. So if I looked at t of +1/2, we already did most of the work. This is 1/2 quantity cubed, that's 1/8, all over 1/2 to the 4th power is 1/16 minus 1. distribute 16, we get 2 all over 1 minus 16, which is negative 15. And so, like I said, that was going to be below the x-axis, and I just tested it to show. And so this is below the x-axis here, knowing that that's our intercept. We can do this. One more piece. To me, this kind of looks like it's symmetrical across the origin. So I could have tested to see if this was an odd function, and I would have known. And if that's the case, then I know that my graph is going to be up like this. Or it's actually going to, I think, faster just to show. Let's choose a number bigger than 1. So let's look at maybe x equals 2. So if we look at t of 2, so 2 cubed is 8, all over 2 to the 4th, which is 16 minus 1. So this is going to give me 8 over 15, which is above the x-axis at x equals 2. And so again, knowing where the asymptotes are and just what that point is, I know that as I get closer and closer to 1 on the right-hand side of 1, it's going to be shooting off to positive infinity. And as we're going off to infinity, we're going to get closer and closer to the line y equals 1. So we have our graph of that rational function by finding the asymptotes, our intercepts, and plotting a couple of extra points. Our next example is f of x equals 8x squared plus 26x minus 7, all divided by 4x minus 1. If we look at this, I guess I could see if it factors. Let's look at 8x squared plus 26x minus 7 and see if that factors. 8 times negative 7, that's negative 56. So I'm looking for something that multiplies to negative 56 and adds to positive 26. Two times 28, is that going to work? Yeah, 2 times 28. One needs to be negative, so it would have to be a negative 2. So negative 2 plus 28 gives me 26, and negative 2 times 28 gives me negative 56. So I'm going to rewrite my middle term using those two numbers. And so let's write it as minus 2x plus 28x minus 7. Factor by grouping. I can pull a 2x out of the first two terms, and if I pull that out, I'm left with 4x minus 1 plus second grouping, I can pull out a 7. And if I do that, notice I have 4x minus 1. So pulling out 4x minus 1, we're left with 2x plus 7. So notice this is setting my numerator equal to 0 and my denominator equal to 0 at the same spot of 1/4. So for our domain, x cannot be negative 1/4. But again, because it sets our denominator equals 0, we have a hole at this point. So notice that we could actually simplify this. And 4x minus 1s go away. And all you're left with is 2x plus 7. Well, 2x plus 7, that's just the line. We can graph that. So I know I have a y-intercept, it's in slope-intercept form. I have a y-intercept at 7. And I have a slope of 2. So if I rise up 2, I would run over 1 to the right. The thing is that I have this hole at x equals 1/4. So I need to figure out what is that y value at x equals 1/4 if I plug it into the piece where I simplified it. And that is where I'm going to put an open circle on my graph. And so let's look at f of 1/4. Plugging in that wherever I see an x, we get 2 all times 1/4 plus 7. Well, 2 times 1/4, that's 1/2. I'm going to need a common denominator. Or I could just say 7 plus 1/2 is 7 and 1/2. But this is 14 halves, right? Which is 15 halves, which I just said is the same thing as 7 and 1/2. So when x equals 1/4 here, we got this 7 and 1/2. So that's about right here, an open circle. And so we have our line. It looks like this. With this open circle at that point. So this one has no vertical asymptotes. It has no horizontal asymptotes because the degree of the numerator is larger than the denominator. And we actually, because we factored this, we were able to figure out what it would have been if we had done long division of 4x minus 1 divided into 8x squared plus 26 minus 7. We would get back 2x plus 7. So we can think of it as an oblique asymptote is the same line that we have as our graph. Other books call it a slant asymptote. Okay, so one more, f of x equals our numerator, x squared plus 6x plus 5. And that's all over our denominator, which is 2x squared plus 7x plus 5. First step, we want to figure out our domain, and we can do that by factoring factoring our denominator, but we're going to need to factor our numerator also. I notice there are 2 numbers that multiply to give me 2 times 5, which is 10, and add to give me 7. That's 2 and 5. And so we could break down rewriting 2x squared, my middle term 7x as plus 2x plus 5x plus 5. I'm going to factor by grouping and just doing this really quickly. So pulling out a 2x from both of the first terms, I'm left with x plus 1. And pulling out a 5 from the last 2 terms, I'm left with x plus 1. So I notice my denominator factors as x plus 1 all times 2x plus 5. So I know that x cannot be -1 and x cannot be, well, 2x plus 5 can't equal 0. So if I subtract 5 divided by 2, x cannot be -5 halves. Let's factor this numerator. And so if we factor x squared plus 6x plus 5, there are 2 numbers that multiply to 5 and add to 6, which are 1 and 5. So notice that there is one value which sets both the numerator and denominator equals 0. And so x cannot be -1. This is going to be an open circle. X equals -5 halves just sets the denominator equals 0. So we have a vertical asymptote at x equals -2.5. Notice that we can cancel, we can simplify these x plus 1s. So let's look at horizontal asymptote. The degree of the numerator is 1, degree of the denominator is 1. The degrees are the same. So I'm looking at the leading coefficient on the top. Which is 1, all divided by the leading coefficient on the bottom, which is 2, which is the same thing we would have gotten if we left it in the original form and hadn't factored and canceled. 2 and 2 are the same, degree on top and the bottom. Leading coefficient on the top was 1 divided by the leading coefficient on the bottom, which was 2. So we have our asymptotes. We are now looking for our intercepts. So looking at f of 0, we go in here and plug in 0 wherever we see an x, we get 0 plus 5, which is 5, all over 0 plus 5, which is 5. So this is equal to 1. So we have a point at 0, 1. Our x-intercept, again, we talked about, that's what's going to set our numerator equal to 0. So 0 is equal to x plus 5, all times 2x plus 5. We can multiply both sides by our denominator. We get 0 equals x plus 5. So x equals negative 5. So we have a point at negative 5, 0. So let's graph what we have. We have a vertical asymptote at negative 2.5. And so we're going to put a dotted line at negative 2.5. We have one x-intercept, and that x-intercept was when x was negative 5. We have an horizontal asymptote, and that was at y equals 1/2. This is 1, y equals 1/2. So we have this horizontal line at y equals 1/2. Okay, so I need to know, is this a graph falling above or below the x-axis between negative 5 and my vertical asymptote of negative 2.5? And so let's go in and plug in a point, and we can plug it into the simplified form. And so if we go in and let's say plug in negative 3, wherever we saw an x, we would get this is equal to negative 3 plus 5, which is 2. All over 2 times negative 3 is negative 6, and negative 6 plus 5 is negative 1. So at negative 3, I have a y value of negative 2. Oops. Okay, so negative 2. So if my point is right down here, this is my x-intercept. I know my vertical asymptote here is at negative 2.5. So this graph here is going to have to hug this as x gets closer and closer to negative 2.5 on the left-hand side. It's going to come up. It's going to hug this line x or y equals 1/2. Just knowing that I had a y-intercept at this point here at 0, 1, I know what my graph is going to look like. It's not crossing the x-axis again. I know I have to hug an asymptote. So this would have to be going upwards. And it's going to start hugging this line, y equals -2.5. And then as we go off to infinity, this is going to hug this line, y equals 1/2. Oops, we have one other piece, and I'm just going to finish it off. X equals -1, we had an open circle. So I need to put an open circle in here. And I could figure out what that value was by plugging it into the reduced form. And so if I look at f of -1 into the reduced form, I would have -1 plus 5, which is 4, all over 2 times -1, which is -2, plus 5, which is 3. So at -1, I have positive 4/3. So 1 1/3. So at 1, -1 1/3. So let's just say about right here. We have that open circle. Okay, so graphing rational functions, you want to find your asymptotes, you want to find your intercepts, you want to plot a couple of different points to see what direction and what the shape of the graph looks like on each side of the intercept.